We are Team MDTS from Hitachi America R&D. It's our pleasure to be here to present to you our approach for the KDD data challenge, a compound model for time series anomaly detection. The challenge is that the 250 time series is a mix of two broad types of anomalies. One type of anomaly is because of noisy data, as we can see in the first plot. The other types of anomaly is due to the different shape compared to the other normal cycles. Plot number 2 to 5 present the different variations of shape-based anomalies. It's difficult to use one single model to accurately identify the anomaly for both types. Therefore, we consider it as two separate tasks. For noisy data, the task is to identify the noisiest cycle. For shape-based anomalies, the task is to identify a cycle that is a fixed amount of data with the most different shape compared to the other cycles. This observation led us to build a compound model. Here is a high-level summary. The model first used a type detection function to map a time series data to an anomaly type, and then it utilized the corresponding module to process the time series accordingly. This diagram shows the specific implementation of the compound model idea. A given time series is first processed by module 1, followed by an evaluation function to determine whether this model gets a confidence prediction or not. If yes, we output a prediction. Otherwise, we use module 2 to re-examine the time series and then make the prediction. Let's first take a look at module 1. The goal is to identify the noisiest cycle. To do this, we define a noise score and identify the anomaly as follows. First, we use the autocorrelation function, which is ACF, to cut the time series into a sequence of cycles. Then we obtain the locally estimated scatter plot smoothing that is lowest for each cycle. Next, we define the noise score as the norm distance between the actual data and the smoothed data in each cycle. And then finally, the cycle with the highest noise score is considered as the anomalous cycle. Next, we propose to evaluate the confidence of Module 1's prediction. Intuitively, Module 1 generated a confidence prediction if there is a few extremely large noise score. Otherwise, it has low confidence about the prediction. To implement this idea, we utilize the interquartile range rule, which is IQR, to check the existence of extremely large values. And if the number of large scores is less or equal to 2, the prediction is confident. Otherwise, the time series is passed to module 2 to be further processed. Let's take a look at module 2. Module 2 aims to identify the location with the most different shape. To quantify the magnitude of shape-based anomaly at time t, we use the dynamic time warping distance, which is DTW, between the best match and the time series data itself. Note that two hyperparameters play a key role in anomaly detection based on this score. One is the sliding window size omega. That is how much data should be used to calculate the DTW distance. The other is the dynamic time warping percent eta. We observe that in sample we observe that ensemble of distance measures over multiple sets of the hyperparameter helps to stabilize the performance. In addition, the reasonable hyperparameters to be part of the ensemble are different for different time series. Therefore, we propose an adaptive way to get the right ensemble for each time series. In particular, we first fix the warping percent at 10% and try different subset of the 7 window lengths. Each subset W corresponding to one score of the ensemble. And then we check whether a high score appears only in one region. If we can find at least one subset W that the outer high score is only appear in one location, then we output an anomaly based on the corresponding ensembled score. Otherwise, we calculate the DTW using other warping percent, based on which we will use the majority vote to identify the anomaly. Let's take a look at some results. In the experiment, 55 time series passed the confidence track of Module 1. For the remaining 195 time series, they were processed by Module 2. The proposed compound model accurately predicted the anomaly location for 87.2% of all the 250 time series. Here are the papers and the packages we referred to in order to build our model. Thank you so much. I'm happy to take any questions.